So as we mentioned before, more fibers contracting equals a greater tension or more force. This is going to help to overcome a heavier load. Okay? Now, activation of the motor neuron activates all the fibers that are in that unit. I want to make that point very clear. We're not recruiting one fiber at a time, one fiber, two fiber, three fiber. We're recruiting by the motor unit. So that motor neuron and all the fibers that it is innervating, okay? Now, there's something called the size principle, and we'll get to that, but it's important to understand that small motor units are for delicate movements, right? Fine movements, muscles of the fingers, muscles of the eyes, your extraocular muscles. Okay, they're not really doing much lifting or force generation, so to speak. More delicate movements. Whereas muscles that are needed for tension, for lifting, right? They are going to be attached to larger motor units. So we have smaller motor units for smaller, more delicate movements, and larger motor units such as your biceps, your gastrocnemius, your hamstrings. They have quite a bit of load that they're going to have to overcome. Okay, so the motor unit size is going to correlate to a few different things, right? The motor unit size. It's going to correlate to the movements, right? And that's what we just looked at. Smaller motor units for smaller, more delicate actions. Larger motor units for larger, more strenuous actions. It's also going to correlate to the diameter of the axon. Okay, the diameter of the axon, right? So if you have a small motor unit with smaller muscle fibers, the nerves that are innervating that motor unit are going to have a smaller diameter. So those axons will have a smaller diameter and smaller cell bodies. Okay, if you have a larger motor unit, let's say innervating your hamstrings, you're going to have larger fibers. The fiber diameter is going to be larger. And those neurons are going to be much bigger. If you've ever compared the sciatic nerve to, let's say, the trigeminal nerve, right? The axons are going to be wider. The cell bodies are going to be bigger for this bigger motor unit in this bigger muscle to generate more force. Okay? So the motor unit size is going to correlate with the fiber diameter. It's going to correlate with the axon diameter. It's going to correlate with the cell body size, and it's going to correlate with the type of movement, right? And the force that is generated. All right. So here we'll talk about the size principle. The size principle. What is the size principle? This is the phenomenon that smaller motor units are recruited first. So if you're trying to lift a load, right, if you're trying to overcome that load and it's a bit heavy, you're going to start recruiting from your smaller motor units before you recruit to your biggest motor units, okay? It's more energy efficient for the body to start increasing in smaller increments. Okay, so let's look at this scenario here. We have a motor unit here, which has 3 fibers attached to it. We have another motor unit with 5 fibers attached to it. And then we have one with 7 fibers attached to it. So the order in which we're going to recruit those motor units is from the smallest motor unit. And we'll recruit that unit with 7 fibers as a last resort. Okay, we're not going to jump to that unit with 5 fibers first. And this is called the size principle. And the reason we do this is because the larger neurons are much more difficult to depolarize. Okay, it's going to take more energy to depolarize this bigger neuron. Remember we said that they have wider, the axon diameter was wider, the cell body was wider. It's going to take more to depolarize this bigger neuron with these 10 fibers on it than it will to depolarize this smaller neuron with, say, 3 or 4 fibers. So the efficient thing to do is to increase in those smaller increments by starting with the smaller motor unit and working our way up as needed. Okay. All right, now the last thing that we're going to talk about here is the velocity of shortening. Okay, the velocity of shortening. And this is basically how fast a muscle contracts and shortens. So this is specifically for an isotonic contraction. And just to remind ourselves, an isotonic contraction is where that muscle is shortening, that load is being overcome, that load is being lifted, okay? And that steady, right, constant tension is being produced, which flattens off the top of that graph, okay? Now we want to mention three things that happens with a load. So the first thing is that the latent period is going to increase as the load increases, right? The latent period. So if you look at this graph, right, this is if we're trying to lift zero load. This is if we're lifting something a little bit heavier, and this is if we're lifting a very heavy load, right? Now notice the latent period here is going to be more for a heavy load and less for zero load. Okay, what does that mean? It's going to take less time for excitation, contraction, coupling to happen to generate force to lift nothing. If the load is zero, that muscle is going to contract pretty easily. It's not going to be that much of a lag, right? The latent period is going to be very fast. If we are lifting a very heavy load, right, which is this graph here, the latent period is going to be a lot longer. We're going to need more calcium in that cytoplasm. We're going to need more cross bridges. We're trying to generate more force to lift this heavier load. So the latent period will be longer. Okay. The second point we want to mention here is that the duration of shortening decreases with an increasing load. Right? The amount of time that the muscle is spent contracting is going to decrease if we're lifting something heavy. Think about it. If you're trying to lift something very heavy, right, how fast will your muscles contract or stay contracted? As that load gets heavier, that contraction is going to be even more brief, right? As the load is lighter, that contraction is going to be longer, more steady. Okay, and we can see that on this graph here as well. When the load is zero, the contraction is going to happen for a much longer time. When the load is its heaviest, the contraction is going to be very brief, right? Very brief to generate force, and then it'll relax right away. The third thing we want to mention here is that the velocity of shortening, how fast that muscle shortens, decreases as the load increases, okay? The velocity of shortening. And that's how quickly this muscle will contract. So let's look at this graph here. At our maximum velocity, okay, is zero load. And that means if we're lifting nothing, we're going to do it pretty quickly. Think about how fast you would lift a box that was empty versus lifting a box full of books. Okay, think about how fast you would walk or run if you didn't have any additional weight versus if you had a backpack and some groceries. Okay, so the heavier the load, the slower the velocity until we get to zero velocity, which is at our heaviest load that we can carry.